Right, so welcome to Math 355, Lecture 24. What I wanted to do today is talk about some applications and connections between group theory and linear algebra. In particular, I want to talk about how do you generalize things that you've seen, and how do you write programs to numerically explore in a reasonable manner. And so there'll be some extra credit coding available today. Okay, so the first is one of my favorite formulas in mathematics, the Baker-Campbell-Hausdorff formula. And so it talks about two matrices, x and y, e to the x times e to the y equals e to the z. If x and y are real, what would you think z would be? So xy real, then e to the x, e to the y equals e to the z implies z equals what? X plus y. If x and y are matrices, hope if you have e to the x, e to the y equals e to the z, z equals, what would you hope? Yeah, it would just be x plus y. If x and y are nice to each other. And so in mathematics, we always start off with a word like nice or good, and then we try to quantify. Can you give me any situation where you think x and y might be nice to each other?
Are we assuming that they are compatible sizes?
Yes. And so implicit in this is, what does e to the x mean? And we'll see later that it only works for square matrices. So we'll assume x and y are the same size. What do you think nice to each other might mean? If you have two matrices, when might two matrices be nice relative to each other? What would you love two matrices to do to each other? So if they cancel each other out, so that means what? But cancel each other in what way? So if I give you two matrices, what might you hope is true about the two matrices? What operation might you do to the two of them? If I give you two matrices, what can you do to two matrices? How can you combine them? You can sum them. Do I ever have to worry about summing matrices? No. Multiply them. Do I ever have to worry about multiplying matrices? Yes. So what might nice to each other be? Well, you can always multiply if they're the same size. What might be a good condition to put in?
Their product is some high product.
Well, what's a nice thing that could happen for two matrices? If I want to multiply them, how do I multiply A and B? Well, how do you multiply two matrices? What do you have to be careful about? If I give you two matrices and ask you to multiply them, what's the thing you have to be very careful about for matrices that you don't have to be careful about for real numbers? We'll assume x and y are the same dimensions. What do you have to be careful about if you're multiplying two matrices that you don't have to be careful about for real numbers? You should know this. No, what's the big thing you have to worry about with matrix multiplication?
It's not commutative.
It's not commutative. So what might be a nice property?
It's commutative.
If they commute. So maybe this means commute, right? And that would include diagonal matrices. Diagonal matrices commute. But maybe more generally, maybe if x and y commute, everything will be nice. So one is we have to figure out what does e to the x even mean? And two, the commutator is defined by the commutator of x and y. You might have seen this before, is xy minus yx. If x and y commute, what is this equal? 0. So this, in some sense, measures how far x and y are from commuting. It's going to be 0 if they commute. If it's not 0, that gives me some information about how far away they are from commuting. We still have to figure out, what does e to the x even mean? What does it mean to take a number and raise it to a matrix? Okay. One of the things you should always be thinking about is the who gives a shit question, right? Why do we care about this? And I was actually talking with a colleague who wanted to use that word in a lecture he's about to give to Williams students during commencement, and says, can I use that word? 50 years ago, no, it was actually on the list of 7 words you cannot say. There are 7 words you cannot say. I'm not going to go through any of the other 6. I think this one has now reached the point where you can say that. Why do we care? Well, one is the discrete logarithm problem. So it turns out if P is prime, Z mod PZ star is a cyclic group. So this is a cyclic group if P is prime. And for us, maybe P is going to be of size 10 to the 400. So it's going to be big. So what does it mean to be cyclic? It means the sum generator, so that I can write this as 1g, g squared, g cubed, dot, 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 all the way up to g to the p minus 2. As g to the p minus 1 will be the identity. And again, all of this is mod p. And so now, it turns out if x and y are real numbers, and y equals x to the n, can you find n? So if you know 2 real numbers, and you know y is x to the n, so you know x and you know y. How could you find n if you know x and you know y is x to the n?
It's the most straightforward thing.
Yeah.
Just divide y by x and see how many times.
Okay, but if n is of size 10 to the 400, that's going to take you a while. Is there any nice way? And again, these are real numbers. So it could be a while before you find exactly.
Okay.
But again, you know, these could be numbers. These could overflow your calculator. What could you do?
Look at x and try to. So we can.
So why is x to the n? That's a product. What should you do every time you see a product? What should you think of? Take the log. So the log of y is the log of x to the n is n log x. So n is going to be the log of y divided by the log of x. For real numbers, it's really easy to find n. If I know x and I know x to the n, I can find n by just taking logarithms. For groups, it's much harder. And so for groups, if I know g and g to the n, what is n? I can't do the log of g to the n mod p over the log of g. I can't do that. That's the problem, is when we're doing things on discrete groups, it's not g to the n, it's g to the n mod p. There's no known nice way. If you can find a nice way to do this quickly and efficiently, be very careful who you let know that you can do this. Right? Very, very valuable in cryptography if you can find a way to do this. This is called the discrete log problem. In the continuous case, the continuous log problem is trivial. You give me an x to the n and an x, I can find n. In the discrete case, even if I know g and g to the n, I don't know a good way to find n. It turns out you can use this to do cryptography. And a lot of cryptography comes down to 2 people agreeing upon a secret, which will then be the basis of cryptography. Maybe it's a letter code, substitution code, where I'm going to shift the first letter by this amount, the second letter by this amount, the third letter by this amount. Now, the most secure way to communicate is the one-time cipher, where 2 people meet ahead of time and they agree on the method they're going to use. never met come up with a secret? And can they do this in public where they're yelling and everyone is listening to them? And the striking answer is yes, there is a way to do this. So two people are yelling, and it's like taunting, like the warden, where, hey, this is what I'm going to do, and this is what I'm going to do. And now all of a sudden we have a secret. So it is required that one person is named Alice, one person is named Bob, and then you have some freedom over the last person. They can either be Charlie or Eve. You have that freedom. Charlie, because it's a C after A and B, Eve for eavesdropper. Okay, so Alice has a secret A. Oops. Since I'm in yellow, I'll write Bob's secret B for Bob. Alice has a secret A. And then everybody knows G and the prime P. So even Charlie and Eve know that. And Alice is going to shout G to the A, mod P. And Bob will shout G to the B, mod P. What does Charlie now know? Now, what else? What has Alice heard? So she heard G to the B, mod P, and Bob heard G to the A, mod P. What can Alice compute? So she wants to compute something that Charlie can't compute, but that Bob can compute and get the same thing. So Alice and Bob want to compute the same thing. What could Alice compute now? She knows A, G to the A, and G to the B. What can she compute that Bob could also compute? So she somehow has to use her secret A. She knows GP, G to the A, G to the B. And Bob knows his secret B and G to the B, G to the A, G and P. What could she compute that Bob could also compute? Well, if she could find B, then that would mean you would have a way of solving the discrete log problem. We don't know how to find the exponent B, so it's safe to shout out G to the B. We don't know a quick way to find B. If Charlie could solve the discrete log problem, then Charlie would know A and B. So what can you do? You know G to the A, G to the B, and you have A, and Bob knows G to the A, G to the B, and knows B. How can Bob and Alice combine these things in a similar way so that they'll end up at the same thing? Well, but if you get G to the A plus B, Charlie can compute G to the A plus B. So you can't multiply G to the A and G to the B. You can do something else. What could you do? Alice just heard G to the B from Bob. What can she do with G to the B? Not multiplied by A. Exponentiated by A.
Oh yeah, and then we get AB.
And so now she gets G to the AB. Well, we'll do it this way. She gets G to the B to the A mod P, and Bob is going to get G to the A to the B mod P. So Alice and Bob share the secret G to the AB mod P. So this is amazing. They're able to share a secret yelling in public. And we're just using some basic facts of groups. Absolutely stunning that this can be done. And this is the basis of stuff like this, of so many problems in cryptography. It is relying on the assumption that it is not easy to find the exponent knowing G and P. If you found a way to do that, then all of a sudden this becomes trivial for Charlie to break, because now Charlie knows A and B. And then Charlie could figure out what to raise G to the A by. Okay, so here is some code, and I'm actually very proud of this code. If I really could, I would put in a lot of comments, but I'll talk about it instead. And then for extra credit, I want you to make this code less efficient as well as more efficient. Okay, so a lot of it is trying to figure out how well do you need to code for something to run in a reasonable amount of time. So what this is going to do is it's going to find all the generators of the cyclic group Z mod PZ star for various choices of primes. So the P is the prime input. So is generator is initialized to be empty. It's the list where we're going to store the numbers that are the generators. And then I'm going to have n go from 2 to p minus 1. I've got to be a little bit careful if my prime is small. If 2 is my prime, then Z mod PZ star is just the identity. So the element 1 does generate. But once my prime is greater than 2, there's no way that 1 would be a generator. So I really shouldn't have 2 here. I really should change this to be a 1. But if I change it to be a 1, then I'm going to have that extra check every single time, right? And the only time 1 can be a generator is if I happen to put in the prime 2. So maybe I don't want to do that and just save time a little bit. What about p minus 1? What is p minus 1 congruent to mod p? Minus 1. So if you square it, you get 1. So the only time minus 1 can be a generator is if p equals 3, in which case p minus 1 is 2, which is a generator. So really, I don't have to check p minus 1 once my prime is large, like 5. So I could make it a little bit better, but that's not going to be significant. If p is of size 1,000, it's not going to be that big of a deal. All right, so the list is initialized to be empty. Current is equal to 1. And then for k goes from 1 to p minus 1, this is the main loop. So I'm going to put this in red. And I want to talk about how we do things efficiently. As a pure mathematician, you don't have to worry about being efficient. You can just say factor the number. But when you try to do something in the real world, factor the number, okay, universe dies a heat death before you do any progress. So how do we do this efficiently? Well, the naive code, which I want you to write for extra credit, is let's see if n is a generator. So I just look at n squared, n cubed, n to the 4th, n to the 5th, n to the 6th, and so on, and see are they all distinct. This is extremely inefficient. If you've calculated n to the 4th, do you really want to start all over and go n times n times n times n times n times n to get n to the 6th? If you know n to the 5th, how do you get n to the 6th? Multiply by n. How do you get n to the 7th? Multiply. That's why I said current equal to 1, and then current is now current times n mod p. So I multiply by n, and then I mod p to keep things as small as possible. So this is going to make the multiplication a lot faster. Get rid of that. See how much longer it takes if you don't do that. And now I have a if then else statement in Mathematica. So I first check to see, is my current number in my list? And if the answer is true, then that means n cannot be a generator because all these numbers are not distinct. And so if n is not a generator, then I want to exit this loop. I don't want to keep computing once I know that n is not a generator. So I'm going to choose k to be p plus 1 larger than the upper bound for the for loop. So I'll immediately execute it and I won't waste time doing calculations that I don't need to do. If, however, it is false, if it's not in my list, then I found another element in my orbit, another element in my cycle, and I'll add that to my list and I'll keep going. And when I finally finish the loop, I then check and see, is the length of my list p minus 1? If yes, great, it's a generator. And then I add it to my list. So this is actually not too bad code. If you run it, it took about 34.7969 seconds to find all the generators when the prime is the next prime after 2024. So Mathematica has a really nice command called next prime. And so I don't have to worry about, well, what is the next prime after 2024? Just have Mathematica do that for me. And here is a list of all of them. And we end pretty quickly. But 34 seconds is a reasonable amount of time. For half a second, it's not worth doing something else. For 30 minutes, I'm going to definitely do something else. I'm not going to just sit looking at the screen for 30 minutes. For 34 seconds, that's enough time to handle an administrative email or two. It's enough time to clean up my office a little bit. It's enough time to do something. So the question is, can I make the code a little bit faster? How far can I go with this code? This is investigating a prime around 2,000. Could I investigate a prime around 10,000? How quickly does this grow? You could do some tests. You could do some plots and look at the runtime. How long does it take to find the generators as a function of the prime? And you could plot that and see how it grows. I would actually do a log-log plot. You have a better chance of finding some kind of nice relationship in a setting like this. There is, however, one simplification you can do that will make things a little bit more efficient. So right now, I have x going up to p minus 1. Part of the reason I'm choosing these topics is this is a great way to review what we learned or we're supposed to have learned this semester. If I give you a group, what do you know about the subgroups of it? Good, so we know by Lagrange, the order of any subgroup divides the order of the group. So if the order of my group is p minus 1, then an element is a generator if it has order p minus 1. If it's not a generator, it generates a proper subgroup whose order is less than p minus 1. What's the largest order you can have less than p minus 1 divided by p minus 2? I don't have to go up to p minus 1. I just have to go up to p minus 1 over 2 plus 1. If all of those elements are distinct, then I've just shown that my number has to have order greater than p minus 1 over 2. And then the only thing that can be is that immediately improves all the way up to being p minus 1. So I don't have to check all the way up to p minus 1. So if p is large, then every time I have a generator, this is going to be essentially a 50% savings. If it's not a generator, it doesn't do me any good to do this because I would have already found earlier. I've got to go one more because I'm not starting at 1. The first thing I check is n, not 1. So I have to go one further. Not a big deal. You can adjust the code a little bit. But every time I have a generator, and if you look over here, there were a lot of generators. That's a 50% savings. So maybe instead of 34 seconds, you might be able to reduce this by maybe not quite a factor of 2 because you have all the non-generators and you're not getting any savings there. But you might be able to knock this down by maybe 30–40%. And again, that's just one small, trivial change in the code. And the runtime can have a huge impact from that. This is one of the things I really want you to get out of the course is if you're going to the point where you have to do some coding, what can you do to code well? Okay. The next is I wrote a really simple code to list all the powers of a number mod p. And for example, if I run my generator program with the prime 7, it tells me 3 and 5 are generators. So let me check. Let me look at the powers of 3 mod 7 and the powers of 4 mod 7. And we see the powers of 3 mod 7 are 3, 2, 6, 4, 5, 1. Yes, 3 generates. And the powers of 4 are 4, 2, 1, 4, 2, 1. 4 doesn't generate. It's always good to check and make sure things are reasonable. I could have, of course, checked this by hand, but why check things by hand when I can just write a simple program so long as I'm confident I can write a program like this? And again, all I'm doing now is just writing a program to give me powers of a number mod p. I'm pretty sure this is not something I'm going to screw up. A more involved thing, I might want to check things by hand. Okay, so let's return to why do we care? Here's another application of the discrete log problem. It's the discrete log problem for elliptic curves. So let me give you an elliptic curve, and I'll draw it like this, say. And again, use your imagination that I'm drawing this really well. I'll take 2 points on the elliptic curve, say P and Q. I draw the line connecting them. It hits the elliptic curve, and then I reflect downward. And this point over here is going to be P plus Q. And we can play the same game as before. We'll have Alice, we'll have Bob, and then we will have Eve / Charlie. So I guess this time I wrote Eve first, but that shouldn't really matter. And so now everybody is going to be told some point on an elliptic curve. Alice is going to have her secret A. Bob is going to have his secret B. Alice is going to compute P to the A and share that with everybody. Bob will compute P to the B and we'll share that with everybody. And then Alice can figure out P to the AB and Bob can figure out P to the AB. And so again, they have a common secret. And again, it's worth noting that we've got to be a little bit careful when we're doing this, that we use fast multiplication. So use fast multiplication. For example, x to the 100 is x to the 64 plus 32 plus 4. We did this earlier in the semester. This was the binary expansion of the exponent. And so this is now the same as x to the 64, x to the 32, x to the 4. We can do this quickly. So x times x is x squared times x squared is x to the 4th, x to the 4th times x to the 4th is x to the 8th, x to the 8th, x to the 8th, x to the 16, x to the 16, x to the 16, x to the 32, x to the 32, x to the 32 is x to the 64. So worst case scenario, x to the n takes approximately 2 log base 2 of n steps. So even if the exponent is size 10 to the 400, we're talking about something around 1,000 operations. You can do that on a computer. We could not calculate 10 to the 400 naively. So if I had to do, p plus p plus p 10 to the 400 times, no chance. But if I can use fast multiplication, I can easily do it in the allotted time. Okay, so now going to exponentials. So if I give you e to the x, the definition of this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. And this is the same as the sum, n goes from 0 to infinity, of x to the n over n factorial. What is e to the x times e to the y?
Wait, well, it's multiplication. It's a product of x, e to the x.
Good. It's two infinite sums. It's the sum n goes from 0 to infinity of x to the n over n factorial times the sum m goes from 0 to infinity of y to the m over m factorial. And let's collect all x to the n, x to the m, where n plus m equals k. So when I expand everything, I'm going to have some powers of x and some powers of y. That should be a y to the m. And so let's collect all of them where n plus m equals k. So what we could do is we could write n equals L, and then m would be k minus L. And if you want, I can go and I can justify this in Thursday's class. This is then the same as the sum k goes from 0 to infinity, the sum L goes from 0 to k, x to the L, y to the k minus L over L factorial k minus L factorial. Now, when you look at this, it should be screaming at you that this looks like something you've seen before. What does this look like? You've got an L factorial k minus L factorial. Yeah, what do I need to put in the numerator? I've got an L factorial k minus L factorial. What should the numerator be? Not L factorial. K factorial, right? If I put in a k factorial over k factorial, then k factorial over L factorial, k minus L factorial, this is just k choose L. And so this sum is going to become the sum, k goes from 0 to infinity. I can pull out the k factorial in the denominator because that doesn't depend on L. I have 1 over k factorial, and I'll have a sum, L goes from 0 to k, of k choose L, and then x to the L, y to the k minus L. What does this equal? What does that sum on L equal?
No, it's a binomial. It's
Yeah, binomial theorem. This is just x plus y to the k. So then this becomes the sum, k goes from 0 to infinity, of x plus y to the k over k factorial, which is e to the x plus y. So this is justifying the notation, okay? It should not be allowed to write e to the x if you can't combine the exponents, okay? So now, given this success, what we can do is we can generalize. So e to the x would be the identity matrix plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus dot, 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 dot. So if I have a square matrix, x squared, x cubed, etc., makes sense. So this is okay if x is a square matrix. And now we can talk about, can we combine, can we multiply two different matrices and figure out what e to the x times e to the y would be? In general, it's going to be hard. But if A and B commute, then e to the A, e to the B would be the sum of a to the n over n factorial, the sum of b to the m over m factorial. Similar to what we had a moment ago, it would be the sum, k goes from 0 to infinity, 1 over k factorial, the sum L goes from 0 to k of a to the L, b to the k minus L. And then this is a plus b to the k as they commute. In general, that's not going to be a plus b to the k. You'll have a to the k, and then you'll have a, b, a, b, a. You can't just combine those things. But if they commute, you can, and then you get e to the a plus b. So if a and b commute, e to the a, e to the b is e to the a plus b. If they don't commute, it's going to be much harder. If a is diagonalizable, there exists an orthogonal Q, which means Q transpose equals Q transpose Q, and a diagonal matrix lambda such that A equals Q lambda Q transpose, or maybe you have the Q transpose on the other side. I always forget which way they want to do things in linear algebra. So let's say we have a diagonalizable A. So let's say A equals Q lambda Q transpose. E to the A is going to be I plus Q lambda Q transpose plus 1/2 Q lambda Q transpose Q lambda Q transpose plus dot dot dot. I can write I as Q transpose. We call Q transpose is Q transpose Q is the identity. What is 1/2 Q lambda Q transpose Q lambda Q transpose? How does that simplify? Yeah, so Q lambda squared Q transpose. Right? What's the next one going to be? It's 1 over 3 factorial Q lambda cubed Q transpose. So notice we can pull out a Q on the left, we can pull out a Q transpose on the right, and we get I plus lambda plus 1 over 2 factorial lambda squared plus 1 over 3 factorial lambda cubed plus dot, dot, dot. Well, so we're basically saying this is now going to just be Q e to the lambda Q transpose. But if lambda is a diagonal matrix, this is just Q e to the lambda 1 dot, 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 e to the lambda n Q transpose. So if the matrix can be diagonalized, we can actually calculate e to the a very easily. In general, e to the a equals the sum of a to the n over n factorial converges for all a. The matrix elements of a to the n grow polynomially in n, so have enough decay from the n factorial. Yeah, the n factorial is going much, much faster. So if you want, I'm happy to go through in detail and show why this converges. This is analysis. I have to resist the temptations to do analysis because this is an abstract algebra class. But as you go deeper in mathematics, they're all connected. And so just because I can write down this definition doesn't mean that this series converges. Matrix exponentials like this are extremely important in mathematical physics and solving differential equations. And so it's worth knowing how all of these come into play. And so I wanted to just show some of these. I'm not going to go into detail on the Baker-Campbell-Hausdorff formula. I'm just going to post it up here so that you can see it. The main thing is if you look at the expansion for what z is, you notice it starts off x plus y. That's good. And then the next term is 1/2 the commutator of x and y. Well, if x and y commute, what's the commutator? 0. The commutator is xy minus yx. So if x and y commute, it's 0. The next term is 1/12 x commutator of x with commutator of xy minus 1/12 the commutator of y with the commutator of xy. So if they commute, they're 0. So you can see good that all the other terms will vanish if they commute. And then if they're close to commuting, the hope is that these higher powers become less and less important as you go deeper and deeper in your expansions. So there's a lot we can do. I'm going to just leave some links here if you want to read a little bit more about groups, especially in mathematical physics. You can actually look at what's called manifolds. These are generalizations of Euclidean spaces. You can talk about coordinate maps. You can talk about groups. You can talk about groups where the matrix elements are continuously varying, where you can maybe even do differentiation and whatnot. The main thing is to know how to pronounce the name of the mathematician who's behind a lot of this. This is pronounced Lie. So if you ever say Lie groups, people know that you don't really know much mathematics. So you should be aware of that. The other thing you should be aware of is if you ever see the phrase real simple Lie groups. This doesn't mean the subject is easy. What do you think the real refers to?
Existing.
Nope. Real numbers. That's what the real is.
Too obvious.
And what do you think simple refers to for groups? We've talked about simple groups. So real simple Lie groups is not a really simple subject. Okay, so just things you should be aware of. I'm not going to go into much detail unless people want me to, in which case I'm happy to talk about this on Thursday. There's lots of different matrix groups you can look at. So unitary matrices form a group. Unitary times unitary is unitary. Orthogonal form a group. You can look at all matrices with integer entries and determinant 1 or -1. That will form a group. So there's lots of things you can do. And what I'll end with today, just because it's not always done in linear algebra, is special matrices and eigenvalues. So for example, A Hermitian is the complex conjugate transpose. So if A equals 2 plus 3i, 6 minus I, 4 plus 2i, and 7, then A Hermitian. So I first take the transpose. So it's 2 plus 3i, 6 minus I, 4 plus 2i, and 7. And now I take the complex conjugate of that. And so I change all the signs in front of the number. So it becomes 2 minus 3i, 6 plus I, 4 minus 2i. And so that's how you would find the complex conjugate transpose. So there's a bunch of special matrices you should know about. So real symmetric is A transpose equals A, and entries are real. Complex Hermitian is the complex conjugate transpose of A is A. Unitary is UHU equals UH is the identity. And orthogonal is Q transpose Q equals Q transpose is the identity. And we'll say entry is real. And recall a non-zero V is an eigenvector of A with eigenvalue lambda if AV equals lambda V. And it turns out if A is real symmetric or complex Hermitian, then the eigenvalues are real. If A is unitary or orthogonal, the absolute value of the eigenvalue equals 1. So these are some really nice results about eigenvalues. And at least in the last case of unitary and orthogonal matrices, you can see there's a group structure. And so we can ask, if I have this group, what can I say about the eigenvalues of the elements of the group? And so what I want to do is I want to prove that the eigenvalues of a unitary matrix have absolute value 1. Is an orthogonal matrix unitary? Yeah. Orthogonal matrices are unitary. So if I show that the eigenvalues of a unitary matrix are 1 in absolute value, what must be true about the eigenvalues of a orthogonal matrix? They must be 1. Now you might ask, maybe they're not just 1, maybe they're plus or minus 1, maybe they're also real. So let's quickly check some things. If I give you the vector V is 1 and I, in linear algebra, you often do V transpose V to find the length. And if I do that, I would get 1I with 1I, which is 1 squared plus I squared, which is 0. This is bad. You never want to have a non-zero vector having 0 length. What we do is we look at V Hermitian V, which would be 1 minus I, 1I, and now we would get 1 squared minus I squared, which is 2. And if you think about it, if I give you the vector 1I, that's kind of like going 1 unit in one direction and 1 unit in a perpendicular direction. Oh, that's my classic 1, 1 root 2 triangle. Yes, the length squared should be 2. That sounds good. Let's say I rotate by 90 degrees. If I rotate my vector by 90 degrees, should there be a real eigenvector? A vector whose direction is left unchanged if I change its direction by 90 degrees? Do we agree that there should not be a real eigenvector? To be an eigenvector, you just rescale the length. You keep the direction unchanged. If I'm rotating my vector by 90 degrees, it's not pointing in the same direction. So the matrix that rotates by 90 degrees is 0, minus 1, 1, 0. We talked about that earlier in the semester. Using the method of divine inspiration, I'm going to apply that to the vector 1I. And let's see what I get. I'll get minus I, 1. Okay, how can I get from 1 to minus I? What do I have to multiply 1 by to get to minus I? Minus I. And if I multiply I by minus I, what do I get? 1. So notice this is actually the same vector as minus I times 1I. So I is an eigenvalue with 1I as the eigenvector. So here is an orthogonal matrix. Its eigenvalue has absolute value 1, but it's not real. So this is a simple proof that the eigenvalues of orthogonal matrices are not going to just be plus or minus 1. Proof by construction. Okay, so let's quickly prove that the eigenvalues of unitary are absolute value 1. So theorem, if U is unitary with eigenvalue lambda and eigenvector v, then the absolute value of lambda equals 1. And the proof is we use U Hermitian U is the identity matrix. So without loss of generality, we can normalize the eigenvector v so that it has length 1. So VHV equals 1. It's not a big deal. If its length wasn't 1, just divide by its length. Now we multiply by 1. V Hermitian V is the same as V Hermitian identity V. I'm just putting the identity matrix. But the identity matrix is U Hermitian U. What's the transpose of a product? The transpose of a product is the the product of the transposes in the opposite. So I can see your hands switching, right? The transpose of a product is the product of the transposes in opposite order. So this is the same as UV Hermitian UV. But because V is an eigenvector with eigenvalue lambda, what is UV equal to? So V is an eigenvector of U with eigenvalue lambda. So what is UV equal to? Lambda V. So we get lambda V Hermitian lambda V. Well, that becomes, when we take the Hermitian, it's the complex conjugate transpose. So lambda is a scalar, that becomes just lambda bar V Hermitian lambda V. I can put the lambdas together, lambda bar lambda V Hermitian V. Well, we've assumed V Hermitian V is just 1. So this is the length of lambda squared. And we started off with a vector normalized to be length 1. So we now know that the length of lambda squared is 1. So if the length of lambda squared equals 1, then that implies that the length of lambda equals 1. So we just proved that unitary matrices have eigenvalues of size 1. And again, there's a lot of things you can do in a class like abstract algebra. If I'm teaching Calc 1, I've got to teach you all the different calculus techniques. I have a lot less freedom in terms of what I want to cover. Abstract algebra, there's lots of different ways you can go. So almost surely, if you take a future class, we'll have done some things that they don't care that you've done. And we will not have done some things that they'll care that you've done. And so there's no way, because different professors are going to emphasize different things. In this class, I wanted to emphasize some of the connections to number theory, some of the connections to cryptography. These are great applications of abstract algebra. Other people might choose to emphasize geometry and looking at reflection groups and stuff like that, and symmetry groups. There's lots of different things you can do. You are smart students. So what you want to do, and this is a good way to prepare for the final, go to a section of the book that we didn't cover. Look at some of the theorems and try to prove them. If you have trouble, talk to me, read the proofs in the book. But you've got to get to the point in your education where we don't have to cover everything. We have to cover enough so that you now have the language so that you can read the rest. You know, at dinner last night, there was somebody at the table who mentioned that they needed a scraping program to cull data from the web, had never done it before, but within an hour after watching some YouTube videos and looking at some files, they were able to do that. That's the goal of our education. It is not to teach you everything. That's why I would much rather cover less material and talk much more about the thought process and about how to do things quickly and efficiently. You know, this is why I really wanted to spend time talking about where was the code? You know, the code over here. How do we do it well? So for extra credit, make this code worse. Don't do the fast way of multiplying. Just calculate higher and higher powers of n directly. Don't exit the loop as soon as you find that it's not. Don't change the upper bound. See how long it takes. See, can you actually get up to the primes around 2000 if you do it like this? And then also see how much better does it make if you replace p minus 1 with 1 more than p minus 1 over 2. See how far you can go. Do a plot of maybe the runtime against p, or probably better, the log of the runtime against the log of p, and try to get a sense of, is there some kind of linear relationship? Can you get some estimate about how far you might be able to go with something like this? And then if it's taking too long, are there some tricks you could do to quickly maybe figure out, is something a generator without calculating everything? What can you do? And so there are some things you could do to make this even faster, which I will leave for later time. All right, so this is a good place to stop.